welcome to the Technical Insights Track 2, our next session. My name is Charlotte Dryden. I lead a visual compute solutions team at Intel Corporation, and I'm moderating this track all day long today, and I'm very happy to introduce our next speaker, Dr. Ioannis Kakadiaris. He is a professor of computer science at the University of Houston, and he's going to speak with us about AI-powered identity and evaluating face recognition capabilities. So he says he can go by Dr. K for short, so appreciate that. So welcome.
So good afternoon, everybody. Thank you very much for the warm introduction. And I want to thank the organizers for their kind invitation. Before I proceed, I would like to know a little bit about you. So how many of us are face recognition system developers? A few. How many of us are face recognition system users? A lot. How many of us do you have a smartphone that uses face unlock? So you're all users, basically, correct? So what I would like to accomplish today is to share with you my suggestions on how you should evaluate a face recognition system when you're planning to integrate it in your application. And I have two objectives for you. First of all, my first objective is to be knowledgeable, to understand what it takes to develop an evaluation rubric for face recognition system capabilities. And second, I want you to be excited about what face recognition can offer to us to facilitate our life. It certainly makes a difference to someone with a last name Kakadiaris because it's very difficult to spell. So we want to use other modalities for accomplishing our goal. So let's stipulate, for the purpose of this discussion, that you have identified that for the purpose of your application, you're going to use face recognition. And you're going to use face recognition either for identification or verification. And by the term identification, I would refer to the process of assigning an identity to an individual depicted in an image. And by the term verification, I refer to the process that you will be able to check whether two images are acquired from the same individual. Usually in the process, we talk about a gallery, which is a database of all the data that we are interested, and a probe dataset. And this is the dataset to which we want to assign a label. Notice that I use the word dataset because you may have either images, one image, many images, or videos, or a mixed set. And these datasets, and without loss of a generality, let's think about images, can be either frontal constrained images in some constrained environment for enrollment purposes, or frontal unconstrained, using the selfies that we all learn to love, and unconstrained in outdoor evaluation scenario. So in a face recognition system, usually there are two components. We have the template generator, and the template generator, the job of the template generator is take as an input your data set, one image, multiple images, videos, or a mixed set media, and generate a template, and this template is stored in your gallery. Then once you get a new data set, you're generating a new template, and you invoke a matcher that will match these two data sets and give you a similarity score, and depending on the application, whether it is identification or verification, we can say whether these images are from the same individual or they give you the ID of the individual. So actually, in this report that was published in November 2018 from the National Institute of Standards and Technology, we have evidence about the exponential accomplishments that we have in our field for the last 4 years. And some of these accomplishments include the fact that we have 15 times difference in facial detection and template generation. The template size has been reduced by at least 40 times. And then the matching speed or the comparison speed has been improved at least 220 times. So I guess naturally the question is, why do you need an evaluation metric, correct? Everything is beautiful. But as you know from your experience, rarely in life you have a choice between a good thing and a bad thing. Usually you have a number of things, and they are almost all good. But you need to come up with an evaluation rubric. You need to understand what are the questions that you want to ask and how you will score each answer. And that's because, at least in that report, there are 127 algorithms, and these are provided by 39 developers. And we know for a fact that there are algorithms that are not included in that report. And if you also look at the top performing algorithms, you'll see that they are all using some sort of artificial intelligence, machine learning, deep learning, so on and so forth. So when you develop your evaluation rubric, you want to make sure that you are thorough and you don't jump into a decision, but you take the time to think not only the criteria, but how you score its answer, because you want to avoid forgetting some factors that might point to some negative publicity like the one that we saw in the Wall Street Journal back in April 2019. So the goal of the meeting, of my presentation today, is to share with you what do I believe you should consider when you put an evaluation rubric together. I will not talk about how you score each answer. I'll be happy to talk to you in private on this. But I'll tell you what are the things that I would think that they are important for you. So basically, the three things that we are going to talk today is that you need to pay attention to your application scenario. What are the challenges that your specific data will bring to the algorithm? And what are your hardware, software requirements or constraints that your application requires? Okay? So let's talk about the application. I'm a professor at the University of Houston, so I had to fly from Houston here, and I strongly believe that I want my face to be my passport. I wanted to board my plane using my face. They know I'm going to travel to San Jose. I wanted to arrive in my hotel and receive a text in the lobby with the information on what is my room number, just go to my room and the door to open using my face. And when I rent a car to go to the airport, I just want to walk in there and get the next car that is available. And we know that the travel industry is slow to adopt AI developments in identity. But I want to bring to your attention what the second largest cruise operator is doing, and that's Laurier Cruise Lines. I have no conflict, so these are examples just to stimulate some discussion. And you can see that they are using computer vision and face recognition for a variety of things. And as they say, their goal is to go from the parked to the car in 10 minutes, so you don't have to wait for a long time in the lines, or save food by planning how much food they need. So what they have to do, of course, is they have to identify, is this an identification scenario or authentication scenario? Is it a verification scenario? Do the application requires them to have this data in different lighting conditions? Maybe you want to have a sensor that captures data during the day and a different sensor that captures data during the night. So are they going to use one sensor or multiple sensors? And in terms of sensors, you all are familiar with 2D sensors and NIR, thermal, so on and so forth. But I want to bring to your attention a different kind of sensor, and that's a 3D sensor. A sensor that can give you not only the appearance of an individual, but also the 3D relief, basically the 3D surface of a face. And these sensors first became available back in 2004, and they were adaptations of medical scanners. They were used for scanning a female breast in terms of preparing for plastic reconstructive surgery. And at that point, they cost about $50,000. In 2015, many of you have tried the structure sensor. The structure sensor gave you wonderful data for 3D with a small cost. And for those of you who have been to the Consumer Electronics Show, you saw again either sensors that you can attach to smartphone, or you saw smartphones that include 3D sensors as part of their sensors on board. Again, no affiliation with the companies that are described. This is just to communicate a message. So application scenario is very important, but you shouldn't forget what is the kind of data? What is your prototypical user? What is their age, gender, skin genotype? All these informations are important. All this information is important when deciding which algorithm you will going to deploy. And of course, how do you expect to be the orientation of the face with respect to your sensor? Will your subjects assume different expressions? Will they have any occlusions, either because they are outdoors or because they are wearing specific items that are customary in the country that you are deploying your system? What are the illumination conditions? Do you have to worry about training bias when you select an algorithm that is trained on one type of data, but you want to try to deploy it on a different population? And is this an attended system or an unattended system? Do you have to worry about spoofing and adversarial attacks? But let's see these things one thing at a time. The most important item is understanding that changing the orientation of the head with respect to the sensor, of course, induces appearance change. So in this appearance change, sometimes people try to capture by having multiple images that will capture this variation. And usually, you will see a plethora of systems. For the purpose of this talk, I chose to compare academic systems rather than commercial systems. You can use the performance that is in the NIST report. But you can see here that one of the challenges is that when you use data-driven algorithms, you want to have extensive training, you want to contain large distributions of poses, or you can choose to generate frontal images, no matter what is the orientation of the head with respect to the sensor. You can generate the frontal images. This is the approach we have developed at the University of Houston, but this leads to higher template generation time, if that's a concern for you. And then there are methods that are depending on the accuracy of your head pose estimation or require multiple models in different pose ranges. Let's see how one can acquire data like this. This is actually a system that we have developed at the University of Houston, and from a single individual, we can obtain 21 images at the same time. And not only the 2D images, but also the 3D images. And we did the 3D because we wanted to have a ground truth about the 3D position of the head at that specific time. So you can see a version of this system. Basically, it has 21 3D cameras, and the subject sits in the middle. And you can be imaged with this system. You can see here that we have about 24,000 data sets from 77 subjects, and we have looked at the issues also of the different resolution, because that's another consideration that you should take into consideration when you develop the evaluation matrix. What is the interocular distance on the faces that you want to detect and eventually recognize? This, of course, is very important, and the performance is different for different algorithms. So from a single data set, we're able to use multiple resolutions here, starting from interocular distance of 500 pixels to the more common interocular distance of 34 pixels. We have created some indoor lighting conditions. For example, what happens when the face is lit only from the left or only from the right, or you have an ambient illumination that does not saturate the human face. And as a baseline, we have developed our own face recognition algorithm that achieves state-of-the-art results. And I'll give you just the steps that are taking place there. The first step is that, of course, we have to find where is the face in the image, face detection. So we do a lot of work actually in a multi-scale face detection, because when you have an image that has multiple faces, each of these faces usually comes in different scales. So you want to be able to do the face detection really, really fast in an embedded vision application. We're able to identify the landmarks. The landmarks gives us the ability then to reconstruct a 3D model. And this is where the coupling comes with a 3D sensor. All this experience that we gained by developing 3D face recognition algorithms now give us the ability from a single image to develop a 3D model that we can use this later for recognition. Once we have the 3D model, then we can estimate the pose, worry about lighting. We have to relight it to the conditions of the gallery in order to have a normalized comparison. Then we can extract what is valid from this specific picture, the valid picture, part of the texture, and then we can generate the pose and illumination invariant features. That's basically our template. And for the purposes of this discussion, let me point out the value of relighting. You will see this value later. So I'm standing here in front of you and say that if I want to recognize an individual, I have to have 21 images? No. The answer is categorically no. I'm standing here to tell you that if you want to know what is the accuracy of the algorithm, you cannot use a single number, because the accuracy is a function of the pose. What is the experiment that you want to perform? What is the pose of the subject in the gallery? What is the pose of the subject in the probe? Let's see a specific example. So having a data set where we have 21 images at the same time allows me to actually do 20 different experiments and quantify the performance of an algorithm in different views. So let me give you an example. Suppose that my gallery is a frontal image, like the one that you see on the right, but my probe has the pitch and yaw of -90 plus 30. What is the performance of this specific algorithm? And if we assume rank 1 as the metric, you can see that the rank 1 performance for this algorithm is 78%. If I want to examine a different scenario, here I have 100%, and I can fill all the columns correspondingly. So you can see that the same algorithm has different performance depending on what is the scenario that you are interested. So if you are, of course, testing frontal to frontal, okay, you have a solution. But if your images in your probe will be always a profile, and the gallery will be always frontal, you want to examine what is the performance of your algorithm for that specific scenario. And that becomes important when you want to compare algorithms. Here, for every cell, I give you the performance of 2 academic algorithms and 1 COTS system, a commercial system. And look at the performance of the commercial system. You can see that if you are in the -30 to 30, maybe this is acceptable for you, 90%. But if you are in the -90, you get 10%, or in some cases 3%. I think this is an important consideration when you make a decision which system, which algorithm you will adapt for your system. Again, we have changes and challenges of expression. Many of us live through the era when we have to take the passport photos not to smile. We don't see the need for this anymore, correct? Because we have developed algorithms that allow us to take advantage of the changes of the expression. This comes at the expense of increased sample size or increased number of data for training data-driven algorithms. Occlusions are an important aspect, and you have to take into consideration what kind of occlusions you expect on your prototypical or archetypical customer. Are you expecting to see a lot of facial hair, or the subjects to wear eyeglasses, for example? And you can see again the comparison of the algorithms, but I want to give you a little bit more specific example. So here is the drop in performance for the same algorithm in different conditions. So here is the drop in performance when we have individuals that have banks, and you can see about 8% drop in rank 1. Significant percentage drop, more than 15% when somebody is wearing eyeglasses. Rather small when you have a mustache and sideburns. So actually here we have examined very systematically all the potential occlusions that one might have, and we're able to rank them based on the effect that they have on the performance of the algorithm. So you can see that eyeglasses have resulted in a 18% drop in the rank 1 performance, followed by wearing a hat, having bangs, sideburns, and mustache. And so that led to basically development of an algorithm we call occlusion-aware face recognition algorithm. I'll be happy to provide you the reference. Is under review right now, where we have developed a system that is robust to a variety of occlusions that you might be facing in your data. The next important thing that I want you to take in consideration is the lighting. The lighting is really important because it can cause two different types of effects. You can have either a perceptual change, you can mistake identities due to changes in the lighting, or you can have changes in the appearance. Again, a lot of work in the academic literature, and training data becomes the limited factor there. What you see here is basically a system that we have developed for mobile face unlock. Sometimes you wake up in the middle of the night and you don't want to turn the light, but then your phone will not unlock because it uses your face, correct? So on the left, you have a low light face image, and then we have developed a pre-processing algorithm that enhances this image to be useful for any kind of face recognition system afterwards. That's a small application that shows you that lighting is really important and can affect even your function in everyday life, because without the proper lighting, some of the mobile phones will not even unlock, and they will ask you to enter your password, correct? So again, this is a system that we have developed at the University of Houston, where we are able to estimate the albedo and the normals, and then reconstruct a well-lit image that we can use for comparison. So, So here you can see the result of this algorithm on different illumination conditions. So the data set that we have at the University of Houston, and we'll be happy to work with you on evaluating the algorithms that you are interested, allows you to get quantitative measurements about the impact of the lighting on the specific face recognition algorithm. And you can see here that with our image illumination enhancement, we were able to increase the performance of the underlying network by at least 3 to 10%, depending on the case. Again, this is on the top of an academic. You can imagine that you can have different backbone, and you use our algorithm on the top. And talking about bias, I'm sure all of you have seen these headlines, and what I want to keep you in mind, for you to keep in mind, is that when you're training your algorithm, you have to keep in consideration what is the population that you're going to test your algorithm. Where are you going to deploy your algorithm? There are a lot of tools that we have in our toolbox as computer scientists in terms of transfer learning and data augmentation. Now, in terms of system design, of course, there is the perennial question whether you want to do the computation at the edge or you want to do it in the cloud. But I want to point out the effect not only on the size of the template, because the size of the template that I can use for my credit card is different from the size of template I can use for my passport, and it's different from another access control application. But also, what is the size of the binary of the face recognition algorithm that you need to deploy? If I have a large binary, how is it going to fit in my smartphone? Do I have enough memory for it to run, for example? And of course, computational speed is always a challenge. We all know about this. Power, again, what are the power requirements of the algorithm that you are using for comparison? And of course, many of you have seen the Commercial Face Recognition Privacy Act that introduced in the Senate in March, and that calls for consent and data security. So I urge all of you to look at the Commercial Face Recognition Privacy Act, because it's my experience that sometimes we develop technology very, very fast, but the policy is lagging behind. And at this point, we are at the point that we have to have development of policy at the same time of development of technology. One of the questions that you have to keep in mind is what are the potential adversarial attacks? Here we had a customer that gave us his app, and he asked us if we can spoof the app both for geolocation and for identity, and we were able to do both at the University of Houston, and that saved the customer from a major embarrassment, if I may add. So this is another thing that you have to test, is what happens when you have geo-spoofing attack. So in terms of the applications, I don't know all the applications that we're going to use, but I can say that they are either access control or real-time screening, or you use it in a forensic environment, or something else. So I'd love to hear what is the application that you are interested in, maybe specialize some of this evaluation rubric. But in closing, from my talk, I want you to remember 3 things. As you consider different face recognition algorithms, please develop an evaluation rubric that takes 3 factors in consideration. Understand your application and its requirements. It's paramount to know exactly what kind of data you will be called to analyze. What is the age, gender, skin phenotype of the individual that is going to be your typical customer? What is the behavior of the customer when interacting with your sensor? And then think holistically about the solution, not only about computational speed, but also what are the memory requirements. And with that, I thank you, and I'll take your questions. Thank you. Yes?
So how would you ask you 3D reconstruction in your Are you using 2D for the face recognition part, or do you have fusion?
Indeed. So face recognition using our experience on 3D-aided processes give us the extra, the last mile that allows us to give state-of-the-art results and outperform the methods that they don't use the 3D reconstruction.
Dr. K, thanks so much for the talk. I'm Reza Rasool, CTO at Real Networks. We are working on computer vision as well. You mentioned early on the NIST results, and most of the companies that are developing facial recognition technology submit their algorithms there. I'd like you to comment on what are the failings of the NIST approach in terms of being able to evaluate facial recognition for real-world applications, and by that I mean in the wild, live video applications. The approach to me seems appropriate for still photo facial recognition, but misses the real-time live video in motion aspect of real-world facial recognition.
Thank you for the question. I would like also to change a little bit. I wouldn't say failings. The NIST report is your first stop when you're developing your evaluation rubric, because there are so many applications, so many requirements, so many data challenges. I don't think a NIST report can cover all the possible scenarios. I think you should start as a first step there in order to reduce the number of algorithms that you will go through your evaluation rubric. Is there room to expand these evaluations? I will offer 2 things. Without having done a comprehensive study. Accuracy as a function of pose. In many situations, we don't have frontal images and we want to have profile images, for example. How does the performance change? And also the size of the binary is not evaluated. You mentioned other things that the NIST report can be improved, and I'm sure if we brainstorm, we can find other things. But I will say that is a great start for you to think which of the algorithms you want to start in your evaluation rubric.
Great, thank you.
Thank you.
Hi, thanks for a great talk. I learned a lot of interesting things here. I just have a quick question on the technology that you mentioned, changing the illumination of a picture. Have you, I understand that might be very hard to do, but have you looked into the ways of achieving the same, but augmenting the data sets with more variety of illumination conditions?
So one of the things that you are pointing out is, do I want to capture more illuminating conditions in my data, or do I want to develop an algorithm that will pre-process the image? So let me clarify that this algorithm is data-driven to be able to augment this. And I always believed that you cannot collect enough data to capture all the illumination conditions that one will face in everyday life. So having a system that has both learning from data and first principles always help addressing some of these challenges. If you allow me for a minute, I always tell to my daughters that I will not be there when they're making all the decisions. I gave them some basic principles, and they should use these basic principles to make decisions. So that's how I see the identity systems. All right, thank you very much.